Hello, my name is Hornbeck. I'm an independent consultant in Salt Lake City. I work for multiple entities in the state of Utah. I've been working in the Uinta Basin since 2007 and was involved in implementing the range-wide monitoring program in 2012. The purpose of the original range-wide monitoring program conducted from 2012 to 2016 was to study threats from oil and gas development that was occurring across the species range in the Uinta Basin. We had 10 Sclerocactus wetlandicus, or Uinta Basin hookless cactus, subpopulations in our study sample comprising 406 plots and 993 individual cacti. We are not addressing Sclerocactus brevispinus subpopulations in this presentation, but we also had 5 subpopulation monitoring sites for that species. The data presented here today are from 6 monitoring sites. 5 are BLM administered and 1 is U.S. Fish and Wildlife Service at the Ouray National Wildlife Refuge. We had approximately every other year monitoring from 2017 to 2019, and no monitoring occurred in 2020. Any missing data points between years were estimated using adjacent observations, basically stem size averages. The 2012 to 2022 sample comprised 267 plots and 1,384 individual Uinta Basin hookless cactus plants. In late 2022, I completed population viability analyses on the 2012 to 2022 range-wide population monitoring data. This figure shows a summary of those results, with the red dotted line indicating deterministic population growth rates for the study sample that I described in the previous slide. The green dotted line is the number of individuals comprising that study sample. We also estimated a stochastic population growth rate using the observed conditions from 2012 to 2022. And all of those rates showed that the population is approximately stable, but you'll notice on this slide that our population growth rates fluctuated quite a bit over that time frame. In particular, with a disturbance event occurring in 2016. And that is shown right here, where you can see that the population growth rate dipped far below the stable range, which is shaded in pink, approximately a population growth rate of 0.95 to 1.05. That population growth rate is actually in the lower 0.7 range. You'll also notice that population size decreased dramatically from that time, from 2015 to 2017, and has rather steadily declined since that time. Also notable in this figure is the population structure along the bottom axis that shows the distribution of individuals in 4 size classes that we used for our analysis. The smallest size class 1, represents seedlings and juveniles. Size class 2 is small adults, size class 3 larger, and of course size class 4 the largest individuals. And it's size class 3 and 4, but mostly 4 that we're going to focus on here today. So as I stated previously, although the population growth rates, both deterministic and stochastic, suggest that the population is stable, changes in the size and structure of our population suggest otherwise. I tested several hypotheses to assess population structure and try and figure out exactly what's going on with the population decline that has continued since the disturbance event in 2016. So I evaluated the total size of large adult cactus, which is some stem diameters, and I believe that total size has decreased since 2012. I also looked at the average stem sizes, so individual stem sizes of these largest adult reproductive cacti, and I believe that these have decreased as disturbance has caused the loss of large stems that are then replaced by multiple smaller stems. As such, I think the total number of stems has probably increased since 2016 in this population. So I took the largest individuals in my sample and looked at the total size of those individuals, the average stem diameters for those individuals, and I looked at survival. This regression figure shows the mean stem diameters of all of the surviving individuals observed from 2012 to 2022, and they're pooled together with a total of 1,335 individuals observed over time. You can see in this scatter plot that there is a strong correlative relationship between the average stem diameter at first observation and the average stem diameter at the next observation, or t to t plus 1. So it's almost a one-to-one linear relationship between the size of mean stem diameters from one time to the next. It's strongly significant with an R-squared of 0.691. So when you look at this figure, the points above the black line are all indicating survival and growth. So those are individuals that increased in size, so the average stem diameter got larger. And anything below the line shrunk in size or retrogressed. So retrogression, as I stated previously, occurs when a large stem is damaged or destroyed and then replaced by multiple smaller stems. So in an average cactus year, we would expect average stem diameters to stay about the same size. So it should be about a one-to-one relationship from year to year. And this is a strongly size-driven population that we have observed since 2012. In the next couple of slides, I'm going to show you scatter plots for select time frames since 2012. And these plots all include mortality, which are the points along the bottom axis that are zeros. So those are stems that are dead. Again, we have the diagonal black line showing a one-to-one relationship, and then we also have trend lines shown as dotted blue lines on each scatter plot that shows the relationship between average stem diameters from t to t plus 1. So the first figure shows survival and growth of stems from 2012 to 2015, the first 4 years of the study. And you'll see that most stems increased in size. There's a large cloud of points above the black line, with a few individuals that decreased, and then of course some normal attrition or mortality along the 0 point. And then the figure below it shows what happened from 2015 to 2016. So this is our disturbance event that occurred in early 2016, around the time of monitoring in June of 2016. And you'll see that, again, we have a cloud of points right along the one-to-one line, diagonal, and then we also have relatively large numbers of individuals that decreased in size, some of them dramatically. And then there's mortality along the bottom axis. Particularly, you'll notice that there's mortality of larger individuals included in there. And also you'll notice that the trend line has dropped. We've gone from a R of 0.322 to an R of 278, which means that there is a decreased relationship in average stem diameter from T to T plus 1. And then I looked at what was going on from 2016 to 2022 in the top scatter plot. And you'll see again that most points are around that one-to-one black line. But we have, again, a lowered relationship in that trend line. Our R is now 0.295, and we have relatively high mortality and retrogression in that figure. So there was a decrease post-2016 overall in survival and mean stem diameter. Then the bottom scatter plot shows the entire study period from 2012 to 2022. And you'll see that the points are now somewhat randomly distributed around that 1-to-1 line. We have lost our relationship there. Our R is now 0.029. This is the dissolution of that stasis-driven size dynamic that we observed early in our study from 2012 to 2015. So our population has shifted from stasis-driven individuals where they stay approximately the same size from year to year or grow to a somewhat random survival dynamic from year to year. So again, I have all 4 of my scatter plots now in smaller size on the right side of this slide just to show how the population has changed all in one group. Some of this is certainly attributable to normal attrition. That's expected. But because the largest individuals are not being replaced in the population, this is not normal population dynamics. We should have individuals that are surviving for long periods of time. This is a long-lived species, and those individuals should be getting replaced over time, and they really are not. So returning to my hypotheses that I tested, the total size of large adult cacti actually did not decrease from 2012 to 2022. There are certainly significant differences between years, as indicated by this p-value, but because replacement of single stems by many smaller stems results in approximately the same size individual, it really confounds this analysis, and it's difficult to assess. However, average stem diameters of the largest reproductive individuals did decrease from 2012 to 2022. Overall, there were significant decreases following the 2016 disturbance event. Since then, average stem diameters have mostly increased, but it's not back to the values that we saw from 2012 to 2015. And then also we evaluated the total number of stems of large reproductive cacti just to see if we're actually replacing large single stems with smaller stems over time. And again, this was significant with a mean increase in average number of stems per individual from 2.16 in 2012 to 2.75 in 2022. So how have Uinta Basin hookless cactus population dynamics changed in the last decade? So there has been a significant decline in the number of large reproductive cacti. Size classes 3 and 4 are shown in the figure below as the darker green bars, and there are 2 trend lines that show a downward trend. We've lost more than half of the largest reproductive individuals. There has also been a significant increase in the number of stems comprising those cactus, which is fine, but as you can see in this picture, replacing a large flowering stem with a bunch of tiny non-flowering stems is not ideal. So high mortality of these large reproductive cactus has shifted the population dynamics from stasis-driven, as we saw in the scatter plots, to now a ruderal population structure, with most of the individuals being either seedlings or small reproductive adults that have considerably lower reproductive outputs than the largest adults. So in conclusion, there are multiple threats acting on Uinta Basin hookless cactus, including widespread oil and gas development, increased densities of invasive annual weeds, and widespread livestock and feral horse trampling that not only damages individuals but alters the habitat structure, particularly soil surface and rock cover, that may result in the loss of growing sites for the species. Returning our population to pre-2016 conditions and population structure and behavior may require active interventions in some locations. In any case, removing or minimizing these livestock trampling and feral horse disturbances really is needed throughout the range of the species, but particularly in core population areas. And I'd love to hear any questions that you have on my presentation. Thank you.